Okay, thanks, John. Afternoon, everyone. I'm Sampath from the Colorado State University, and I'm the site director of the Next Generation PV Center here at CSU. And the title of my talk is Cat-Telluride Photovoltaics for Sustainable Electricity Generation. And cat-telluride PV is a thin film coating on glass that converts sunlight to electricity. And from sustainable, I mean both economic and environmental considerations. And we have been involved in cat-telluride research since the late 80s. And the funding for our research comes from the National Science Foundation, which is what you see here, and also from the Department of Energy. The outline of my talk is going to be introducing utility-scale electricity generation with cat-telluride photovoltaics, and we'll compare the cost of electricity generation by different methods. And in this talk, I focus on utility scale primarily because a large electricity generation is in the utility scale. Residential is becoming more important, but this talk I will only focus on utility. The second, we will compare silicon photovoltaics to cat-telluride PV. Silicon PV is the largest used today, but cat-telluride photovoltaics has substantial manufacturing advantages compared to silicon PV, and we will compare to cat-telluride PV. And the third section, we will talk about advancing cat-telluride photovoltaics so that the cost of electricity is reduced further, and then I will conclude. This is an example of a utility scale installation with cadmium telluride photovoltaics. And this was built by First Solar, and First Solar is a part of our industrial advisory board. And they have joined us since 2012 and have been quite active in the center. And this particular installation is in Agua Caliente in Arizona and produces about 290 megawatts at noon. And roughly it can satisfy about 50,000 homes' electrical needs. And here is an example of a utility scale installation. There are three more installations that are shown here from the desert Southwest area. And the Topaz farm is the largest one. It is the biggest in terms of such installation. There is this Nacho Springs in New Mexico, and looked at before. These are other installations in the Southwest, and there are a few more, but I'm just showing three here. Now, it is not just in the U.S., it is installed worldwide. There are many installations around the globe, and totally about 10 gigawatts have been installed worldwide at cat-telluride photovoltaics, and it is expected that 3 gigawatts will be added in 2016. The cost of electricity is more important, and ultimately what matters is the cost of electricity from cat-telluride photovoltaics. And here, this slide compares the cost of generation with the cadmium telluride. Before. On the y-axis, you have the cost of electricity from different methods in dollars per kilowatt hour. And the first two are comparing coal and nuclear, which are as base load power plants. The one in pink here compares electricity generation with natural gas, and then diesel. And the last here is the cadmium telluride photovoltaics shown here in the orange color. The best estimate, the most recent cost from cat-telluride photovoltaics is 3.87 cents per kilowatt hour. And Bloomberg reported that this is the lowest priced electricity in the nation. And the costs are decreasing quite substantially, and they have actually come down by nearly 75% in the last 4 years or so. So I'm going to use this 3.87 number to compare with the rest. And you see that the 3.87 compares quite favorably to electricity made from coal and nuclear, and is very favorable compared to producing from natural gas, and even more favorable producing electricity from diesel. The current big market that the cat-telluride photovoltaic fields, like the one I showed you before, are for substitution for gas peaking plants. So utilities that have gas peaking plants can also have cat-telluride fields, and if these fields are producing, it is cheaper for them to use this electricity, natural gas, to run the gas turbine engines, and that is mostly how the market has expanded for utility scale installations. So moving on to talking about comparing silicon photovoltaics to cat-telluride. And silicon photovoltaics is the largest in terms of use today, and that is more purely because of historical reasons and also subsidy from the government of China that has led to the much more wider use of silicon photovoltaics than cat-telluride PV. But intrinsically, the cat-telluride photovoltaics has some significant advantages compared to silicon photovoltaics, and I will describe that in the next few slides. So here we are looking at the advantages of cat-telluride photovoltaics over silicon PV. And cat-telluride competes effectively with silicon even when silicon is subsidized. And the estimate from our U.S. Department of Commerce is that they have imposed dumping margin up to 165% on Chinese silicon, and here is the reference for that from government sources. So that's roughly how much there is subsidy of silicon in the PV industry. And for semiconductor reasons, the cadmium telluride requires 100 times less semiconductor material, and the semiconductor can be 100 times less pure, which provides a significant advantage in terms of cat-telluride photovoltaics. And it's much simpler automated manufacturing process, and I will briefly describe the process for making cat-tel versus silicon next. And for the same module area, cat-telluride produces about 11.2% more power than silicon, and this has to do with the temperature coefficient of the two semiconductors. And interestingly, there is less cadmium emission from cadmium telluride modules than from the manufacturing of silicon. And this is because if the energy requirement for making silicon modules is quite high, and currently the way we produce our energy, if you take an average, the amount of cadmium emission from producing that amount of energy is more than the amount of cadmium that is encapsulated in the cadmium telluride modules. Initially, there was a concern about raw material limitations, but currently those limitations are not considered to be any limitations at all, and this includes tellurium, which is somewhat rare, but there is enough being found and discovered to use it for the needs. So in the next set of slides, I'm going to describe what it takes to make a silicon PV cell. Now, the manufacturing of PV modules involves making the semiconductor from the natural minerals. The second step involves making the cell from the semiconductor material, and the third step is making modules from the cell. I'm just going to talk about the second step, which is converting the semiconductor material to a cell. And cat-telluride has significant advantages in the manufacturing of the semiconductor material itself and also converting the cell to a module, but that will be not part of this discussion. So I'm just going to compare what it takes, if you have semiconductor material, what it makes to make a solar cell, first for silicon and then for cat-telluride. A silicon solar polycrystalline, multicrystalline silicon solar cell looks like this. There are many types of silicon solar cells, and here I'm just going to look at the multicrystalline silicon solar cell that is the most widely used, and it's a polycrystalline material. And here is a cross-section of the cell. And starting from the very top, you have the silver contacting the front. There is a AR anti-reflection coating. There is a small region of the silicon that is made N-type. The wafer itself is usually P-type silicon. There is a P+ doping put at the back that enables to make good contact, and there is silver at the back, and that is the back contact. And voltage and current comes from the top silver contact to the bottom silver contact, and the total thickness is in the neighborhood of about 150 microns or so for the whole cell, and you need that thickness to convert most of the sunlight to electricity. The starting material for silicon is semiconductor grade silicon, which is usually 7/9 pure. And in this particular case, you start with P-type material. Now, there is quite a bit involved in making this material itself, but I'm not going to be discussing this in this talk. So once you have the material, usually it is made into an ingot, and the typical size of the ingot is about 50 centimeter by 50 centimeter by 25 centimeters. So you're looking about 2 feet here in terms of dimension. So this is a fairly large vacuum furnace into which you load the silicon material, and you pull a vacuum, melt it, and cool it slowly. And typically the process time from the starting feedstock material to an ingot is roughly in the neighborhood of 30 hours or so. The next step involves sawing the ingot into manageable blocks, and here you're looking at a diamond saw that takes that ingot and slices into blocks. And the next step is to slice the block into wafers. And this is usually done by a wire saw with abrasive slurry. And nearly about 50% of this pure material is actually lost during the sawing process on an average. And that's a fairly significant waste. And this is the sawing of the block into wafers. Now, the process of making the wafers creates a lot of defects on the surface. The abrasive process leads a lot of defects. So these wafers have to be etched. And then the etching is followed by a texturing process that creates pyramid-like shapes on the surface to trap the light. The next step involves coating of this phosphor compound on this wafer, and you can see the grains of this polycrystalline wafer material. The phosphor compound is coated to make it, that is the N-type dopant. And the next stage is to anneal this coating into this furnace. And this step is about an hour or so to anneal and diffuse the phosphor into the surface of the wafer to convert diffusing phosphor atoms to create a N-silicon layer. As we saw in the structure before, the PV device involves a P-type wafer with a small N-type region on the surface. And that is what is being produced in this process step. And then the coating that created the phosphor compounds have to be removed, and there is a etching involved to remove the phosphor compounds. And this particular process of doping the wafers also dopes the edges, and the edges can lead to some shorts if they are not cleaned. And here is a plasma cleaning process to remove the doping that has been happened in the edges of the wafer. The next step in making the cell involves coating with AR, and usually these coatings are silicon nitride-based coatings that reduce the reflection from the silicon surface. And this step is followed by screen printing the front, and you see some silver being screen printed on the front. This is what collects the current from the front surface. The next is screen printing aluminum at the back. The aluminum is the P-type dopant, and the screen printing aluminum at the back makes a P+ doping. And subsequently, screen printing silver at the back, which is the back contact. And the last step in making the cell involves firing all these pastes together, the paste that is for the front contact, the aluminum at the back to P+ doping, then the screen printed silver, and this is what it involved in making the cell for silicon material. And the next I want to talk about what it takes to make a cadmium telluride solar cell. Now, the cadmium telluride is not made into a cell and assembled into a module the way we do it in silicon. So what I have done is extracted a very early process that we had in the lab for making 3x3 cell to demonstrate what it takes to make a cell in the cadmium telluride technology. And as it says here, the semiconductor is fabricated at full module size. The full module size today is 2 feet by 4 feet. And that streamlines the manufacturing, whereas in silicon you have to assemble all these cells into module. And this particular process that I'm going to describe was commercialized by Avant Solar, but others are proprietary, but very similar in a sense of how they work. And here is the cross-section of a cadmium telluride solar cell. It starts with a glass with a transparent conducting oxide. And this particular glass and TCO are fairly low-cost soda-lime glass that is made on the float line. And the TCO itself is also made on the float line itself. Then there are two films that are grown on this glass. It has been typically cadmium sulfide till very recently, and we have found out that mag zinc oxide works a lot better than cadmium sulfide, and I will talk to you about that. Then cadmium telluride is the absorber where the sunlight comes in and creates electron-hole pairs, and there is a metal at the back, and between the metal and the transparent conducting oxide in this case is where you generate the voltage and current. And the cell thickness from here to here is about 2 to 3 microns. So it's fairly small thickness of material compared to the silicon process. Now the machinery to produce the cadmium sulfide coating, the cadmium telluride coating, and a bit of heat treatment and doping the backs is shown here. This was an old system we had in the lab that would fabricate 3-inch by 3-inch solar cells. But this, about a 6-foot-long machine, would do the cadmium sulfide, the cadmium telluride, the heat treatment, and back doping. And the whole process took about 20 minutes from front to back to complete. And you can see the schematic of this process in the next slide here, where the glass comes in, it's heated. The first step involves heating the glass from room temperature to about 550 C, and this is done in about 2 minutes. The next, the glass moves to the cadmium sulfide deposition, where a thin layer of cadmium sulfide is sublimed onto the glass. Then it moves into this, where cadmium telluride is sublimed onto the glass. And there are steps involved in subliming and removing the cadmium chloride. This is not left as a film. This is just as a flux aided to reduce the defects in the process. And then we developed this quite extensively, where you can introduce very small amounts of copper, typically 1 to 2 monolayers of copper into the device to dope the back, and then the material comes out. So and the other advantage of this particular process is that this doesn't require a very hard vacuum. Vacuum generated by simple mechanical pumps are good enough. And all the process heads for doing all of this are very similar, and it's a lean automated machine, and the cycle time that we have used is about 2 minutes per station. So it stays about 2 minutes in each case, and in about 15, 16 minutes you have a whole device that come out except for the metallization at the back. So this completes the process of making the N layer, the P layer, the doping at the back, and improving the material by this cadmium chloride treatment, and except for the back metallization. And the back metallization is done by a sputtering process, where here is a load lot. You come in and deposit the metal at the back for the sputtering process. So this essentially completes the manufacturing of cadmium telluride solar cell. And as you can compare between silicon and cad telluride, this reiterates some of the earlier points, that cad telluride photovoltaics requires 100 times less semiconductor material, that can be 100 times less pure, 7/9 in the case of silicon, 4/9 in the case of cadmium telluride. And total process time for silicon is somewhere north of 32 hours. And some of them are fairly hard vacuum processes, wet chemistry processes, versus about half an hour for making the cadmium telluride PV cell itself. And most of these are simple thermal sublimation-based processes and require not very hard vacuum or stringent requirements. And so that's another big advantage. And it's a simpler automated process for cadmium telluride where you can go from glass to a finished module actually in a space of about 2 hours rather than much longer time for the silicon case. So much streamlined process, no cell assembly, and you process directly on large areas. Silicon, you process small areas, then you assemble into a larger area, whereas the cadmium telluride, you can actually do it on large areas from the start. So this all leads to lower capital cost, labor cost, and energy needed for cadmium telluride PV. And so the summary for this section is that the cadmium telluride photovoltaics has substantially better manufacturability than silicon photovoltaics. And this is needed as we go further out and want to make our energy less and less with carbon sources. So we will need much larger production. So the next station is advancing of the technology of cadmium telluride photovoltaics. And here in the advancing, what I mean by that is what is the next research steps involved in improving the cadmium telluride technology. And I'm going to talk about two major areas that we work here at the center of the site. One is to improve the efficiency of the conversion, which means have a much more efficient conversion of the sun's energy to electrical energy, and also a way to improve the package. All of this has to be sealed against moisture and the elements, and we have a fairly substantial effort in improving the packaging, and both of them are intended to reduce the cost of electricity further. Now, most of the research we do, we always keep a clear line of sight to manufacturing and industrial implementation. And the small system that I showed you before was actually converted to a machine for processing 2 feet by 4 feet glass by this company, Abound Solar. This was spun out of CSU. And it will go from a glass to a completed module in a space of 2 hours. And it was fully integrated. There was no need for human intervention from the loading of the glass to the unloading of the module itself. It allows very high degree of automation. So here are the proposed devices that we are investigating. Where we are currently is the technology is right here, where we take this commercially available glass with transparent conducting oxide and put this magnesium zinc oxide buffer that we work quite a bit to develop. The cadmium telluride is the absorber, and these are back electrodes, which in the lab we sometimes use just a carbon binder and a nickel binder, but in the industry it's mostly done by sputtering, and we are ourselves moving towards that soon. And what we have demonstrated and verified by the Newport verification process is that we have demonstrated an efficiency of conversion of 18.3%, which is probably the highest that has been reported for this particular glass in the literature. And this compares very favorably in terms of conversion efficiency with multicrystalline silicon. And if you input the advantages in terms of the higher temperature or the lower temperature coefficient for cad telluride, it's actually better than silicon in terms of converting sunlight to electricity. And the current effort is in this structure that is here, where we have the glass TCO, and there is something to be gained in going to a more transparent glass and a more transparent conducting oxide rather than the Tech 10 glass that was used here. And that effort is currently underway, and maybe use another buffer integration and magnetic oxide. Now, all this is to improve the current to the device. Then we have the cadmium telluride absorber, and big amount of research right now is the magnesium telluride electron reflector, as we call it. And we are also exploring some organic semiconductors for doing this function. And then again, the back electrode contact is this carbon and nickel spray. So this is the effort in the laboratory currently, and we are moving towards doing a multi-junction. A single junction only uses a small part of the solar spectrum, and quite a lot is not converted, whereas a multi-junction taps into the different parts of the energy spectrum. And the prediction is that we can get up to 33%, and potentially even more as time goes on, as we learn how to work all these things in a better way. But one of the things we want to do as we transition from this simple single junction to more advanced single junction to multi-junction is we want to keep the manufacturability of the process so that we have this automated advanced manufacturing process. So we don't want to use processes here that are too complex to be put into manufacturing process. We want to do this all in a very scalable manner so that we can transition it to this. So I want to briefly describe the CSU cat-telluride program. And this is the device efficiency focus, and then we'll later on talk about the packaging focus. So currently what we are engaged in is to take this layer, which usually was a glass with TCO with the cadmium sulfide and cadmium telluride, and we're working on two major improvements. One is an alternative layer, which we saw before was magnesium zinc oxide. It improves the front window layer, and that is to improve the transmission and improve the device current. And then this higher band gap cad magnesium telluride material, which we call as electron reflector, and the purpose there is to improve the device voltage. So we have, over the years, as I said, we have been involved in this since the late 80s, and we have developed some very unique set of processing tools, completely optimized and geared towards the cadmium telluride research. And this is the workhorse, and the primary cell fabrication system is what is shown here. And it's a linear cluster tool where we put our substrates in this position, move it through magnetic arm using this low gate valve to introduce the substrate and remove the substrate. And we can go into any one of these processes, heater, cad sulfide, cad telluride, or the cad chloride, or the back contact. We can vary the time. And this is all in one single vacuum where we have the substrates, and all of these are closed with shutters so that when you are not depositing, you are not contaminating one station with another station. And this is a workhorse system, and we can produce about 200 small area devices in a day. So we have explored a large number of process conditions and processing strategies to improve the cad telluride device. So for the first year, the magnesium zinc oxide result that is shown here, it's still done on the Tech 10 glass with the TCO. And when we put this material, magnesium zinc oxide, with this cadmium telluride absorber, you see some significant improvement in the performance. The blue curve is what it was with just plain cadmium sulfide. The green is with mag zinc oxide, followed by cad telluride. And here are the efficiency numbers. So we have gone from 13.3% with the cadmium sulfide window layer to now verified and certified 18.33% with the mag zinc oxide layer here. So the front improvement is quite a bit underway, and there may be something to be gained by improving this interface between mag zinc oxide and cad telluride, and that's being worked on. Now, in addition to processing devices and testing devices, we have done a large number of cross-sectional transmission electron microscopy, which is somewhat difficult thing to do, but we have had excellent collaboration with the Loughborough University in UK, and we have probably produced the largest amount of cross-sectional TEM studies, and they have illuminated a large number of details about this process, and probably would be very much necessary as we go further. And here is the cross-section TEM of a device. Here is the mag zinc oxide layer in this white region here. Here is the cadmium telluride, and this is one large grain that goes from the mag zinc oxide to the back. And it is this large grains without intervening grain boundaries that leads to very good performance in terms of device. So here is the schematic for what we are trying to do at the back, having an electron reflector to increase the voltage. And the electron reflector is a higher band gap material at the back. And what that does is we ideally would like to create a barrier in the conduction band so that the minority carrier electrons can be reflected away. And all the modeling suggests that we should be able to pick up a fairly significant amount of voltage gain by putting this layer at the back. And the predictions are that we can go from our current 850 millivolts to somewhere in the neighborhood of 1.1 volt. Now, this research is well underway. We haven't seen these improvements yet, smaller improvements with smaller thicknesses, and we're optimizing the process so that we realize this full voltage gain that is predicted by theory. Now, the higher band gap material that we have chosen is cad magnesium telluride, short form written as CMT. And in order to produce this material, we have developed what is called as a co-sublimation process. Here we have one sublimation source sitting on top of another sublimation source with passages and valves and what have you, so that we can have different amounts of the vapor from these two coming in, and we can lay down this cad magnesium telluride films. Now, this ternary alloy scheme is not just restricted to magnesium alone. There are potential possibilities with selenium, zinc, and there is some advantage to running under excess cadmium or excess tellurium. And this whole thing has been added with metallo-organic injection so that we can add other elements and also dope the material. And so potentially the amount of different materials we can look at here is quite enormous, and that's what we will be needing to make the advanced single junction and the triple junction. And what is shown here is that if you run this magnesium source hotter, you can add more and more magnesium and increase the band gap of the material, and then as the magnesium content is lowered, you get a lower band gap material. And one of the fortuitous observations here is that when we deposit this cad magnesium telluride layer on cad telluride, we see that the interface is quite continuous at atomic scale. There is no abruptness between these two layers, and this is kind of needed to make this whole thing work electronically. And you see this at this atomic resolution TEM, and also you see this in the electron diffraction patterns, which are quite similar, and all of these results comes from the University of Loughborough. Good quality of CMT done on cad telluride. Now, what I have described so far is the advances we are working on in the efficiency. There's one other large improvement that can be done is to actually improve the thin film module architecture. The idea here is to improve the encapsulation so that we can demonstrate a 50-year life and reduce the cost of electricity. And I will show you how much this leads to in later on. But the design that we have come up with, and this has been actually done on a commercial scale in a modified way at Abound, and since then a lot of refinement has happened to improve the module architecture. What it involves is two glass plates with a perimeter seal involving silicon. Now, the current designs do not use a silicone layer. They use organic polymer here, and organic polymers degrade under UV, and there is a potential possibility with the current structure which the silicone layer avoids. The second step is to have a polyisobutylene material which is very low in moisture ingress, so that very small amount of moisture gets in. And here is an optimized polymer material containing desiccant so that you can have this 50-year life. And in addition to the improved life, there are many other benefits. This has got a 4 times improvement to moisture ingress, reduced manufacturing time. This whole thing can be put together with 30 seconds compared to the current encapsulation process that takes 15-20 minutes or so, and a much smaller manufacturing footprint area. And there is about a 2 cents a watt, which doesn't look like much here, but in this business, it's quite significant to reduce the material cost of this whole package design. Now, this package has been put together and has been tested. So here is the new method I described to you before, tested for a large number of hours in what is called as a damp heat testing, where there is high humidity and high temperatures, and you look at the power output of the module as a function of time, And as you can see clearly here that it goes on up to 5,000 hours with not much of a degradation. But the current method that is used in the industry today, you can see that they don't last that long. They don't employ all of these advances that has been come from this process. They do pass the 1,000-hour requirement. So if you were only looking at 1,000 hours, which is the requirement from the IEC test, they all pass that 1,000-hour test. But there is now thinking in the field that to go to a 50-year life, we may want to extend this requirement not to 1,000 hours, but go on up to 4,000 hours, and that is the old method, and this is the new method that we are currently working on. Now, what does all these improvements that we are working on lead to in terms of cost? And as I showed you before, the current lowest cost of electricity is 3.87 cents a kilowatt hour, and the current average cost is about 11 cents a kilowatt hour. So now if we just zoom in on this area and look at what the improvements will do, if you go to a 50-year module life, and this is all calculations from the administration in the Department of Energy, and this is the reference from which these numbers come from. So if you have a new 50-year module life, it will drop the cost of energy by 21%. And if you have a 25% effective a triple junction cell, that will reduce the cost by another 24% in LCOE. And so potentially, we could drop this 3.87 to 2.13 by these advances. And as you see, this 2.13 is quite substantially below the current average cost of electricity, which is about 11 cents a kilowatt hour. So the opportunity with cadmium telluride is to go to 2.1 cents, which is about 80% reduction over the current national average electricity cost. So this is the research group that is working on cadmium telluride at CSU. This is a slightly older picture, but nevertheless gives you a feel for about, we have close to about 24 dedicated folks who are involved in various aspects of this research that I have described to you before. And this group works on cadmium telluride. The funding mostly comes from NSF and DOE, but First Solar and FION Plus have been quite helpful in providing us support so that we get all these other projects. I haven't mentioned FION Plus before. Part of the success of cad telluride goes to these folks here. They are the ones who are very significant part of the supply chain in terms of producing cadmium sulfide and cadmium telluride. And recently there is quite a bit of support that has come to the lab from the state of Colorado also. So the conclusions are that cad telluride PV is cost competitive for electricity generation today in many utility scale applications in many parts of the world. It has substantially better manufacturability than silicon photovoltaics. And the opportunity exists to go to 2.1 cents a kilowatt hour or 80% reduction over the current national average in terms of electricity cost. So I want to conclude and leave you with this beautiful picture. And here we all feel that cadmium telluride is truly a gift from nature, that this thin a material converting this much amount of sunlight to electricity with this easy a process to produce. And that's all I have, and thank you very much for your attention.
Thank you, Sampath. I just wanted to point out that we have one question right now that was typed up during your talk, and we'll open it up after that to additional questions. But if you want to open up the, there you go. If you want to just take a look at the chat window there on the left, there is a question about TCO coated glass.
Okay, let me read the question first. I heard that the TCO coated glass occupies about half of the material cost of any type of thin film manufacturing. Is there any particular reason this cannot be reduced? We have not worked on it, so I would have a hard time answering this in a very succinct way. but I'm sure that this is definitely a place of interest. Few points here that we have a 3 millimeter glass on top, and you kind of need the 3 millimeter to withstand hail and the static load, and there are quite a few requirements that is needed there. There may be opportunity to improve the TCO transmission. The current glass that we use only transmits about 85% in the spectrum of interest. Now, that may actually take the cost per area up, but may reduce the cost per watt. That's the best I can say. Any other questions, John?
What does he have in mind for organic?
Sampath, we've got one here from UT.
Hey, Sampath. This is Brian. I was wondering, what do you guys have in... Hey, great talk, by the way. It was awesome. What do you guys have in mind for the organic electron reflector?
Well, we had a visiting faculty member who came from a university in India that we have worked with. And Amit is here. I will let him answer. He's been working with this on the organic semiconductors that have been put in.
So at this point, we have some very preliminary results on using a few different semiconductor compounds. To name a couple of them, it is spiroamidol that is used for perovskites and other something P.PSS with low and high conductivity. Many others that we have tried, we have got some early good indications that we would like to capitalize on. As of now, we haven't seen a major effect what we would like to see as an electron reflector, but with lower amounts of copper in the bag, we have seen the device is able to actually come back to the baseline performance even with less amount of copper, and those are some of the good indications that we have, and we are further working on improving performance with organic. Does that answer your...
Thanks, Amit. Okay, we've got one more here from UT Austin. It's forthcoming.
Hi, Dr. Sampath. I have a question on the tandem arrangement which you showed.
Okay.
You were using nitrogen doped zinc telluride, right? Is it for electron reflector between each junction?
The details of the device for the junction is very, very conceptual right now. So I don't want to say that we are fixed on either zinc telluride nitrogen or anything else. But that's just, we put that as a placeholder at this point. We may find other materials as we go along that works. But basically, we want a tunnel junction, as Tushar is saying, between each of these junctions.
Okay, thank you.
Okay, one more.
Sampath, this is Brian again. Your magnesium zinc oxide buffer layer, do you think that would also work in SIGS devices?
Can you repeat that question? I didn't get it.
Yeah, your magnesium zinc oxide layer, do you think that would also work in SIGS devices as a replacement for cadmium sulfide?
Yeah, zinc actually, the original concept, the original idea for magnesium zinc oxide that Jason got actually came from CIS. Actually, the CIS folks have had more success with zinc oxide than cadmium sulfide. Yes, it should work.
Great, thanks.
Okay, are there any other questions from the other participants in the room, or if you'd like, you can type something in the chat window, or if you'd like to speak up now, please feel free. Okay, well, it doesn't sound like we have any more questions at this time. I'd like to thank Dr. Sampath and the researchers at CSU for their hard work on this project, and Sampath for giving a really great talk. We'll continue this seminar series going forward. Occasionally we have internal meetings, but we're going to continue to open them up to the public frequently going forward. So if you liked this presentation and would like to participate again in the future, please keep an eye on our webpage. That's nextgenpv.org, and this video will be archived on our YouTube channel. Thanks again for tuning in, and thank you, Sampath.